probably fifth time or so I'm in Argentina, but I still like it a lot, and the more often I come, the more I like to come. So thanks again. What I will do in the next 45 minutes, because Detlef isn't there, so he gave me his 20 minutes, is to guide you essentially through one experiment which we did about 4 years ago. So, and this is an experiment where, on the one hand, we wanted to understand, as the title says, plant-environment interactions on a systems level, but also it's really a learning example for us, because we realize that we have to develop a number of new concepts, of new ideas, of new algorithms, and so on and so on. So, and I'll guide you through where we are. So it's an ongoing project, it's by no means finished. Just maybe to add, because I think from Mark's talk it already became very clear, our institute in total is interested in biomass and plant growth. We follow different routes, but a main one, kind of common denominator, is metabolism. And we in my group, we, in addition to doing technology development and metabolomics, also use metabolomics for developing maybe diagnostic tools for predicting or modeling plant growth, plant biomass, and also in quantitative genetic approaches. But I will not touch on that today, but rather on this one project. So, kind of motivation. I mean, not all of you know this, I guess, but just to make it very clear, and I think Mark again also said this. So plants are, of course, exposed to many different and sometimes very rapidly changing environments. And this environment probably doesn't change so rapidly, but it's a very complicated environment. Now, unfortunately, I mean, what would you do when you would be in the desert and you get thirsty? You would just go home, right? A plant can't do it, so that's a problem. So a plant, when it is exposed to a change in environment, the only chance it has is, of course, to rewire its entire biochemical and physiological and molecular networks. And that's what we're interested in, the rewiring or the response of a plant as a system toward the changing environment by changing the wiring of the network. Let me also, because it's a systems, I put systems in the title, also gives you quickly some definitions the way at least we or I understand systems biology. Of course, it has two arms. The one is a theoretical arm, which you can read here, and the other one, of course, is a experimental arm, where you try to extract as many parameters as possible, molecular parameters with a high resolution from the given biological system under study. And of course, I think it's very important to stress that this has to be done in a time-resolved manner. This, I think, is key whenever you really want to understand a biological system. So, and I'll also come to that in a minute. Also, because many people like or dislike systems biology, and I think it's simply fair to say that systems biology will never prove anything. It's just a very nice generator of hypotheses. And it's a novel approach for generating hypotheses, which otherwise you couldn't derive it. So that's the way we understand it. Of course, you have to prove it by genetic or chemical genetic means. So, choice of the experimental setup, just to at least get that clear, what system we are looking at. There are many environmental parameters. Mark talked about a couple of them. And of course, light and temperature are the parameters which are most rapidly changing in a normal plant's experience. So just imagine you go outside, there's some shadow because some clouds are coming in front of the sun. So there's different light intensity, then there's wind, that means a different temperature, and so on and so on. So these changes are very fast and are fluctuating all over the time and over the day. And therefore, we thought these are interesting. Of course, they're also experimentally very well manipulable. In addition, productivity is also to a large extent determined by photosynthetic performance, which again is influenced by light and temperature. So we decide to look at the response of plants to changing light and temperatures in a time-resolved manner. The experiment we did, as said, is one experiment. It was a pretty big experiment, and it involved about 20 people just for the sampling. The sampling actually was a key point. Once you have the sample, you put that at -80, and then you can work on the samples. But doing the sampling in the right way is a key point. Otherwise, you just measure something which is really of no relevance. So we, of course, went back to the model system, Arabidopsis thaliana, wild-type plants, and we exposed them to 4 different light intensities and 3 different temperatures. Of course, all of them coming from a common pool, kept under one light and under one temperature. So these are 8 different conditions. Then we harvested 6 biologic replicates, total of 22 time points for all 8 conditions, and in total this was about 1,000 samples, which were then subjected to transcriptomics using classical Affymetrix chip array design, chip analysis. So as said, we did this experiment a couple of years ago, and also metabolomics, where we applied all the 3 platforms we're having, primary, secondary, and lipidomics. So the experimental design again, we start out with a pool of plants, about what's probably more than 1,000 plants, Arabidopsis plants, 21 degrees, 150 micro-Einstein conditions, and we changed them, kept the temperature, but exposed them to different light conditions, as you see here on the light. So darkness is the extreme light, it's not present, and 400 micro-Einstein is some some light stress already, and also intermediate lights, but kept the temperature. And on the other hand, we also kept then the light condition and put them either, we kept them at two light conditions, either in the darkness at 4 degrees and 32 degrees, or at the normal light at 4 degrees and 32 degrees also. So in total, it's 8 conditions. And then we took samples after, of course, time point 0, then after 5 minutes, 10 minutes, and then every 20 minutes and every 20 minutes until 360 minutes, which is a linear time series, and another is a log time series, another 10 times, which has some statistical relevance. Okay? Now, just what are still the goals and where are we? At the end of the day, of course, we want to get an integrated view of the response on the metabolite transcript level, identify novel pathway genes, identify novel metabolites serving as signaling compounds important for the adjustment of the system, and of course also, which is still tricky, but I'll to show you where we are, identify gene regulatory networks. So today I will cover just a comparative analysis of the response on the metabolite versus transcriptome level, the usefulness of metabolic networks reconstructed on experimental data for hypothesis creation, and also where we stand with reconstruction of a gene regulatory network. So let me start with the first part. Just to give you a glimpse of the experimental data, I will not show very many of those. So these are kind of original data. You see 2 metabolites over here, glycine and fructose. And now this is a busy slide, so I go once through this color code. What we always have, we have the abbreviation. Well, you probably can't read that. So the first is always 21 degrees and normal light, then 21 degrees and dark, then 4 degrees light conditions, 4 degrees in the dark. Then it's 32 degrees in the light, 32 degrees in the dark, and then it's low light and high light. And this is a typical highlight response. You see the glycine, which is a metabolite, goes up very, very fast after transfer. This and on the x-axis is always a time series, without giving you the details now. You see the glycine, for example, increase very much under highlight conditions, but also in 4 degrees light, which also is very similar to a light stress condition. So this is fine, just showing you the data, and you see this is a form of a box plots because it just shows the, incorporate all the 6 biological replicates. You also see something here for just in exemplary fashion for some transcripts. So this, for example, is a heat shock transcript, and you see this is the 21 degrees light and dark, 4 degrees light and dark, and this is 32 degrees light, 32 degrees dark, and this is 21 degrees low light and high light. Exactly what you anticipate, of course, that these transcripts only pop up under heat shock conditions. This is simply showing, yes, my experiment was done in a reasonable way. This is a clock series, and this is just a cold-induced factor and so on, dark-induced factors. So we convinced ourselves that the data are valid. This is well, you see those colors. That's exactly what you should see. And the only impression you should get is, again, these are the different conditions. The first number is always the temperature. The second is the light intensity, or dark, light, dark, low light, and high light. So you see simply that many things happen on the metabolite level. It's always on the x-axis is the time series. And you see, of course, that certain this is something that on certain conditions, such as the 32 degrees darkness, there are more changes than under other conditions as compared to the normal conditions, and this is exactly what you would expect, okay? But you see there's a fast response of the system to its disturbance by moving it from either by changing the temperature or the light conditions. Of course, this is not the way really to look at the data. That was the point here. Yeah, okay. So we then applied a couple of what we call descriptive statistics. And this is a principal component analysis, hierarchical cluster analysis, and so on and so on. So in order to at the end of the day, what you do is you kind of reduce complexity of the data sets and try to look at the data still. And this is a principal component analysis of the transcriptome data here and of the metabolome data. And again, it's a busy slide, but the color coding is by now maybe understood. Blue is always 4 degrees, and reddish is always 32 degrees. And let me just go into one example here. You see here a number of dark red numbers, 4, 5, 6, 7, 8, and so on and so on. And this is, when you go to this legend here, this is 32 degrees dark conditions. That is, you have a condition which after 4 and 3 is over here, and 2 is over here, which already after 10 minutes moves out of the main cluster of all the other conditions. So the system already after 10 minutes is very, very different based on pure statistical terms. And what you also see is there is a unique trajectory. You see the train is also excited. There is a unique trajectory which never intermingles with any of the other conditions, okay? This is, for example, is the 21 degrees dark condition, so that's 10 degrees lower. And again, you see there's a trajectory which doesn't intermingle with anything else. And even more, you see the kinetic series is represented in this trajectory. So 4 is after 20 minutes, 5 after 40, 60, and so on and so on. Okay, these are the two. Cold conditions. Again, you see cold and again forms two trajectories which again are not intermingled. So the system very fast finds its kind of own and specific state. In a similar way, though it's a little more busy, you can also see that in the metabolome data. And I will just make one comparison. This yellow stuff is highlight conditions, and you see where is the control, it's the grayish stuff is remaining over here. This already after 5 minutes, the metabolome data allow to distinguish this state, highlight conditions, from all the other states. So it's a very fast responding system. That's the message I want to give over. And again, very specific, because again, this system doesn't intermingle with any of the others. We also asked the question then, what is the more diverse response? Is it a response more diverse on the transcriptome level or on the metabolome level? So to this end, what we did is we did a pairwise comparison of all transcript data against all transcript data for all different conditions, for all different time points. Now, what you would expect is, just to understand this representation, essentially it's a distance matrix. What you see is there's a bluish line over here, in the middle that's a diagonal, and that is a self-self comparison. And of course, self-self means it's the same, so it's 1. However, when you also see that, for example, the red stuff, which is very different, there's much more red stuff in the metabolite representation as compared to the transcript representation. Again, therefore suggesting that the metabolite response is much more diverse, is much faster, and more specific for the response of the system. So far just for the comparative analysis. Now, this is all funny, and descriptive statistics, can you learn anything for biology? So for that, we did one approach. You can do many. We reconstructed networks based on experimental data. Now, what do I mean by this? Essentially, what you do is very simple. Let's say, look at two metabolites like shikimic acid and phenylalanine, and what you do is then you ask whether or not they correlate. That is, for all the different data set points, you put the one on the y-axis, the other on the x-axis, then you do a regression and ask the question whether or not there's a significant correlation. Now, what you see here is, and this shows rewiring, that, for example, this shikimic acid phenylalanine pair in the 20 degrees dark condition is a negative correlation, whereas in 20 degrees highlight is a positive correlation. So indicating there's a clear rewiring, of course, of the system, of the flow of the metabolites under these two conditions. Now, you can do that for all of the metabolites, and then you end up with networks, which are funny and maybe interesting to look at, and the only thing you should see is they are different for the different conditions, okay? Can you use them or is there any biological sense in these networks, and if anything linked to physiology? And so we asked the question, when we look at these different networks, how many new connections, edges, so to say, do I need to introduce to transform, let's say, the 21 degrees dark network into the 21 degrees light network, and introduce a number of changes as a similarity or distance measure? And when you do this, you end up with a surprising result. At least I didn't expect it. So these networks follow environmental parameters. That is, the network for 21 degrees dark is most similar to 21 degrees low light, most similar to 21 degrees light, and then only comes 21 degrees high light. So it's a clear ordering, and this order reflects the change in physiology. So somehow in the network, and this is a pure topology question of the network, it's a number of edges you have to introduce or you have to delete in order to transform the non-network, which is experimentally reconstructed, into another one. This topology measure reflects some physiological environments. We found that interesting, surprising, the same you see here for the temperature. You can then ask, well, maybe there are conditional networks that could be more interesting. There must be conditional networks, there must be conditional connectivities within the network. Conditional means they are only present under one or two conditions. And if so, maybe you can learn something from that, okay? We've done similar work in E. coli, and that was quite rewarding. So I'll give you two examples for this, what you can learn back to biology. There's raffinose is a compatible, it's a sugar alcohol, and it's since long known or postulated to be important for cold adjustment of plants. When you put plants to the cold, they make more raffinose as a kind of the idea is as a kind of a solute, compatible solute. Okay, so you see this is a part of the biochemical pathway. Now this is just a box plot. When you put plants in 4 degrees light for raffinose, you see. This is the short time series. So from this you would say, well, there's not very much of a change, right? It's more or less staying constant because the raffinose response is a very late one. You see that as an increase in the steady state level only after about 20 hours, much later. However, when you do the network reconstruction, then there is a part of the network which only pops up under 4 degrees light condition. In this network, in the reconstructed network, raffinose is indeed linked to galatinol, galactose, and myoinositol. So this suggests this is a much more sensible, or not sensible, sensitive, maybe indicator for some biochemical mechanisms in network analysis, which again, of course, allows you to postulate hypothesis, that is, that raffinose biosynthesis might be important. And actually, this is true. Now, another example is we looked at connectivity of amino acids. And you see this is, again, based on experimental data, as said before. So when they are co-regulated or co-changed and you give them an edge, that means they are co-regulated. So at 4 degrees darkness, you see some linkage. 20 degrees darkness, you see more. And 32 degrees darkness, you see that many of the amino acids are correlated. Okay? Now, we zoom in. When you zoom in into this cluster at 32 degrees, and you see that it's not only a cluster containing amino acids, but also some parts of the TCA cycle, of the tricarbonic acid cycle. So you see pyruvate, you see GABA, most important, and there was a third, and succinate, which was the third one. So now amino acids are linked in a positive sense with, in a positive correlation with the TCA cycle intermediates. What could this mean? So then, of course, we go back to the transcriptome data, and what we see under these conditions, 32 degrees darkness, there's an overrepresentation, if you do the overrepresentation analysis against statistics, of protein degradation genes popping up after about 1 hour, okay? Now you can put these two observations together and come up with a model, and the model would say that under darkness, which is not overly surprising, of course the plant misses photosynthesis, it still is high temperature, 32 degrees, so what it does, it really starts to chew down the proteins and use the building blocks as a reservoir for the TCA cycle. You then go back to the individual data, and indeed that's what you find. So this is just leucine as one of the amino acids. You see it's increasing at 21 degrees darkness and 32 degrees darkness, not so much under any of the other conditions. And if you go really into the transcriptome data, you see that the leucine degradation pathway is indeed also increasing all the genes of this pathway. So I think I'm running a little out of time, but how much time do I have? 3 more minutes? Okay, let me then at least give you the principle for the third part. So we are, at the end of the day, interested in reconstruction of a gene regulatory network, where we integrate both transcript data and metabolite data and use it as a hypothesis creation for suggesting biochemical pathways and, of course, feedbacks and so on. So let me at least give you the concept. So the workflow. Of course, we have data. And first, we, of course, have to determine with using a lot of statistics. As a rule, we do permutation tests, about 1,000 permutation tests, to determine the level of confidence. Which genes change under which conditions. And of course, we have a time resolved, we have a kinetic data set, so we always ask when is the change initiated. And then we use very simple, two simple approaches. The first one is a temporal logic, and the second is the event strings alignment. Now, what does it mean? And end up with a graph. Temporal logic is really simple. It essentially means when a transcript, the first transcript which changes can influence the next one, which comes later, but not the other way around, which is not true. We know feedback, but nevertheless. So when A is induced before B, then A can influence B, but not the other way around. So if you have this series, for example, you would say gene A influences all the other ones, and gene D only can influence gene D. Now, we are in the fortunate situation that we have 8 different conditions with always time series. So we now ask for robust temporal logics, okay? That means we look at the second experiment with a different environmental condition, and now we see that